Okay, thank you very much. So thanks for being here. We're going to talk a little bit about how we run transformers on our IP. I'll go fast because we only have 10 minutes. Market trends. I don't think I have to tell you that everybody wants to run AI, so you know that. We move on. What are the challenges for running AI, right? It's moving to the edge, so low power, no news, but performance keeps going up. So you want a lot of performance and low power, not nice. And one real problem is that the models just keep moving much faster than any of us in this room can build silicon. So these AI guys keep inventing something every 6 months. And maybe the best of you can tape out a chip in 2 years, but most people tape out a chip in 3 years. So there's a clear mismatch between how fast they invent stuff in AI and how fast we produce silicon, right? And so this brings us to the need for flexible and adaptable AI solutions, right? And we need a new thing, right? And this is our new thing, and it's in our booth. Come to talk to us if it doesn't make sense. But what we've done is decide that rather than have an NPU and a separate GPU from a known vendor in the UK and a core from other vendors that we don't like because they're not RISC-V, you put everything together, right? And you have all the AI under control of RISC-V. So the key thing here is that there's a single software stack, right? There's an out-of-order CPU controlling the whole thing, the little green CPU. And the green CPU controls the vector unit and the tensor unit. So you're not sending data from vector to tensor and from tensor to core and from, none of that. It's all controlled by RISC-V. So you get the following benefits. If you've done any AI programming with these other models, you know you'll be doing DMA copies left and right. It's horrible, right? So here, there's no DMA. You have this one unit that does everything. Number two, you notice that there's a single software stack, right? Everything is RISC-V. So you don't get a software stack from vendor A, a software stack from vendor B, and another from vendor C, and then your software team has to produce something together. No, quite the contrary. It's all RISC-V. It's all a known programming model, right? Now, because these things are all together, there's zero communication latency, literally zero. Right? I didn't say zero power, that'd be lying too much. It's low power, right? Because the data is right next to each other, right? And it's scalable because if I tell you, okay, this thing can do 2 tops, half the room here will walk away and say, oh, I needed 50. No problem. You take this thing and you replicate it 25 times and you will get the 50 tops you want. So we want this IP that's easy for our customers to replicate as many times as they need to hit the performance that they want to hit, right? That's our goal, right? And we say this thing AI future-proof, and that's a little bit more difficult to convince you that it's future-proof, but it is our fundamental concern when we try to make sure that our customer is making a big investment in us, it's making a big investment in their silicon. How do we help them protect that investment? And the answer is, this thing is a CPU. It's a CPU with a very good vector unit, or the best vector unit in my opinion, and a very good tensor unit, actually the best in my opinion. But it's all controlled by a RISC-V CPU. So you can run 3 key instructions, if then else, and you do call and return. And if you are in programming, you know that with those 3 things, you can build any program on the planet. So I can guarantee you, and I will not be wrong, that 3 years from now, this thing can run the software that they will invent. Maybe we will be missing some feature to make it go fast, but I can guarantee you that your software investment is protected, right? So that's a key thing when we have worked really hard to unify everything under RISC-V and provide this IP that's ready, pre-validated, so it goes well. And there's one last thing there that's called gazillion unit. What the hell is that? All this is great, fantastic. Let's say you're all sold out on my talk here, but these things consume a tremendous amount of data, right? You all know that ChatGPT, even I don't know, Llama 2, 7 billion parameter. it's 14 gigabytes of data. So this thing is not useful if you cannot move data from memory into this block. And that's what the Gazillion unit is doing. It's bringing a ton of data from memory into the unit non-stop, so that that beautiful tensor unit or that beautiful vector unit is actually doing useful work, and it's not starving for data, right? So the magic sauce that brings everything together is this Gazillion unit, right? And I can turn this around and say, when I get a customer and ask me, hey, how can I run AI models? What software stack do you have? Can I run transformers? Can I scale? Can I run future models? Future, I already convinced you, I'm sure, that it's dual. Scalable, I told you, we replicate this thing, right? Can I run transformers? Absolutely, you can run transformers. So let's go to the first one, software stack. What software stack do you get with your RIP? Well, we chose one that's actually done by Microsoft, right? So, and donated to the Linux Software Foundation, which is called ONNX. And ONNX is a really strong runtime environment. All the frameworks you know and love, PyTorch, TensorFlow, all of them export to ONNX, right? And you take an ONNX model and you run it on our software stack. And technically, for those of you that know, this is called the ONNX runtime, right? So the ONNX runtime is the thing that's going to run all of this. And we've optimized the runtime to make use of the picture I was showing before. So make use of the vector unit and make use of the tensor unit. So our customer doesn't have to do anything. Take a model, sure, they have to quantize and do a million things that the AI guys do, but that's our customers' job, not ours, right? And once they have ONNX, they plug it in and it runs, right? So we want to make the experience really easy. They get RIP, they get a good software, and they go, right? And how much time do I have? Oh, 4 minutes. I can torture you for 3 minutes. Real quick, to demonstrate that this is not just PowerPoint, right? We are running something like Llama 2, the 7 billion parameter FP16, and to show you a little bit of the flavor of what happens and why this technology is needed and why this is why you want these three elements connected together. We run Llama 2 and we looked at the top operators, and you see matmul and then concat, sigmoid, and all those things that you guys should already know. If you run it on a scalar RISC-V CPU, you get the first column, 99% of the time in matmul. Everybody in the audience knew that already. Okay, fine. That's performance one, right? When you add the tensor unit, in this case we put the 1 teraop tensor unit, you get an incredible speed up of 170 times faster. And the thing that's interesting is that then matmul is only 20% of your time. So now it turns out that those activations that looked absolutely unimportant when you were running on scalar, suddenly they're 80%. And that's why in our all-in-one, not only we have a tensor unit, which all of you expected, but you need a vector unit. Why? When you now couple last column, the T1 plus the vector unit, the V8, don't worry, come to the booth if you want to know the names. When you do that, you get that extra kind of 3x speed up from 170x to 470. You might say, well, that's not good enough. But my point is that what's more important is that 55-45. Now you have a balanced solution. Now you have something that is using the vector and tensor equally. So if you know Amdahl's law, and you should know, and if you don't, go back to study. Amdahl tells you now you're in a good spot. Now you're balanced. Now you can scale. You can replicate this thing, right? Which is exactly what we do. And when someone asks us, well, but I'm a little bit confused. How do you scale your thing, right? We say, look, you take this thing that's at the bottom, which is what I was showing, the core, the vector unit, and the tensor. And in this example, I'm showing you 8 copies. And you could run some cores up there. And of course, we would like those to be RISC-V, but there's people that insist on having ARM there. It's fine. We can still do that, right? But the key thing is that from the main cores, the ONNX runtime can fire all the requests to those acceleration cores at the bottom, and that's where all the AI is happening in a balanced way. You don't like 8, put 16. You don't like 16, put 32, or 32 is too much, put 2 of them, right? So that's the choice of our customer that's scaling the solution, right? I discussed that, so I'm gonna finish here. we honestly think that with our IP, the major concerns of if anyone in the room is trying to do an AI chip and wants to buy IP, come to us because we have the software stack, we can run all the models from today, and we guarantee we will run models 3 years from now. And that is a big, big plus of the way we're doing things relative to other competitors in other spaces that have fragmented solutions, right? And Kendra coming, yeah, we're ready for that too. So, that's probably going to be next year, but we're ready. And with that, 10 minutes. Thank you very much. Thanks for listening. Oh, and come to our booth, of course.